Alright, we're in section 8.1. This is example 3. Again, I just pulled a problem out of the textbook. This is problem number 17 from the exercises in section 8.1. And you might want scratch paper, or you might have enough space on the slide. So I'm going to go up to the top here. This is number 17, which is example 3 from section 8.1. It says, a simple random sample of size 12 is obtained from a population with a mean of 64 and a standard deviation of 17. Now, right away, something should be alerting you. This sample size is not very big. It's not greater than 30. It also does not state anywhere that the population is normally distributed, so we really don't have good foundation for normal distributions. So part A is asking what must be true regarding the distribution of the population in order to use the normal model to compute the probabilities involving the sample mean. So for part A, they're wanting you to notice that the sample size is not big enough. So 12 is not greater than or equal to 30. Therefore, the population must be normally distributed. That must be true. Otherwise, we can't use normal CDF, we can't draw a bell curve because we don't know if the population is normal or not. So we're just going to assume that that's true. And then assuming that's true, describe the sampling distribution of X bar. So again, we want shape, we want center, and spread. Now shape, we're just going to assume that it's normal. We're going to assume that the population is normal so that we can assume that this sampling is going to be normal. Really, that's dangerous in real life, but for this exercise, we're just going to assume that it's true. The center will be at the mean, so the center of the samples will be around 64. And the standard deviation of the samples will be 17 over the square root of 12. Now this is not a pretty number. Let's see, 17 over the square root of 12 is approximately 4.91. Again, I would not use the rounded value. I would just use the fraction, the standard deviation over the square root of the sample size, and do not use the rounded value. We don't want to over-round in this course. So just use the calculation, not the result. Alright, part B. Again, it says, assuming that these requirements are satisfied, determine the probability that the sample is less than 67.3. So we'll do a normal CDF. Less than 67.3, so we'll go from negative infinity to 67.3 using the true mean of 64 and the adjusted standard deviation 17 over radical 12. So I would type it in like that. I would not use the estimation. So we're going to do second bars, normal CDF. We'll go from negative infinity to 67.3. using the true mean of 64 and the adjusted standard deviation. You just type in 17 divided by the square root of 12 and just use a double parentheses to close it, and that should give you the result. 0.7493. Which is a pretty big value, but if you think about it, we're going from negative infinity past the true mean to 67.3. So again, if you draw the curve in shade, it'll help you verify that that number is reasonable. And then part C, I'm going to fold this back here. Part C, assuming that the requirements described in part A are satisfied, determine the probability that X bar is greater than or equal to 65.2. So again, we'll use normal CDF. This time we're going greater than or equal to 65.2, so we're going to go from 65.2 to infinity. The mean is 64, and we're going to use the adjusted standard deviation. And type that in. Again, if you need to draw the curve to help you determine your lower and upper bounds, that's fine. Hopefully you can kind of visualize it in your head, but if not, feel free to draw the curve. So 65.2 to infinity. 64 is the mean, and again we'll type it in exactly and get our result, 0.4034. So this runs just like Chapter 7, the normal CDF, the lower bound, the upper bound, drawing the curve, all of that is the same as Chapter 7. The only thing that changes is that we use an adjusted standard deviation based on the sample size. Other than that, it's just like Chapter 7. Alright, I have one more example in this section. I called it example 4, but I really just pulled it out of the textbook. It's number 28 in the exercises of the textbook. So this is example 4 for section 8.1, but it's number 28 in your textbook. I'm going to clear off my calculator. It says Burger King's drive-thru. Suppose that cars arrive at Burger King's drive-thru at a rate of 20 cars every hour between noon and 1 p.m. A random sample of 40 one-hour time periods between noon and 1 is selected and has 22.1 as the mean number of cars arriving. So, I don't see anything about normally distributed, but our sample size is 40. It says, why is the sampling distribution approximately normal? So part A, and that's because the sample size is 40, which is greater than or equal to 30. That's why we can say that it's approximately normal. What is the mean and the standard deviation of the sampling distribution? Assuming that the mean equals 20 and the standard deviation is the square root of 20. Alright, so it says what is the mean and the standard deviation of the samples. So the mean of the samples would still be 20. The standard deviation of the samples would be radical 20 over, so radical 20 is a weird standard deviation, but that's what they gave us, over the square root of 40, which, let's see, radical 20, close parentheses, divided by radical 40, close parentheses. It's about 0.7071, somewhere in there. So, part C, what is the probability that a random sample of 40 one-hour time periods results in a mean of at least 22.1 cars, which is the one they got in this example. So, at least 22.1 cars, that would be x is greater than or equal to 22.1, so we'll do a normal CDF from 22.1 to infinity. And the mean is 20, and the standard deviation is going to be radical 20 over radical 40, so type that in carefully. Normal CDF, 22.1 to infinity, mean of 20, standard deviation is the square root of 20 divided by the square root of 40. Make sure to close parentheses or stop the square root between those, and then a double parentheses to close it. You get a very small value, 0.0015. And is this result unusual? Yes, it is unusual. And what might we conclude? Well, a couple things could be true. Could be true that the average of 20 is not accurate. It could be true that you just had an exceptionally busy time. It could be true that they miscalculated the sample. So all kinds of things could be true. But 22.1 is unlikely. So they were either extremely busy or the true mean is actually greater than 20. So we'll discuss that further more in chapter 10. So those conclusions, just kind of think about if something's unusual, then something weird's going on. So don't worry too much about those conclusions. We'll discuss those more in chapter 10. Alright, so that is sampling distributions for means. Again, very similar from chapter 7. Now we're going to get into sampling distributions for what's called a proportion. This will be fairly new. It's a little different, and I'll try to make it as clear as possible. It's just a different type of average. It's just called a proportion instead of a mean. So a proportion is the same thing as a relative frequency. So we're looking at relative frequencies or percentages instead of averages. It is a desired outcome divided by the total in the sample. So we have a new notation called p-hat, and this is instead of x bar, we have this new notation called p-hat. And it's the letter P with a little triangle hat on top. And it is your desired outcome, which we call x, divided by the total in your sample n. It is actually a ratio or a percentage. And it has some different properties. However, in the long run, it works just like a sample mean. It just has a few separate properties, just some different characteristics. So hopefully this will become familiar as we go through this. It has the same idea as a mean, a shape, center, and a spread. The shape of a distribution for p-hat is approximately normal, provided these other two conditions are true. So I'll talk about the difference between the two in just a minute. This new condition, if n times p times 1 minus p is greater than or equal to 10, which we discussed, I believe it was at the end of chapter 6. If n, sample size, times the proportion, times 1 minus that same proportion, is greater than or equal to 10, and this other condition, which is a little strange, the sample is less than or equal to 5% of capital N, and if you remember, capital N is the population size. So if the sample is less than 5% of the population size, if both of these conditions are true, we can say that the shape is approximately normal. And we'll practice calculating those. It's just an exercise in crunching numbers, but it's different conditions than means. The center of the sampling distribution is the true proportion. So just like means, where the sample of all the average of all the samples is equal to the true mean, the average of all the sample proportions is equal to the true proportion. So P is the population proportion or percentage. The spread's going to be a little bit different. The spread of a sample proportion is P times 1 minus P divided by the sample size, and the whole thing is square rooted. So it's calculated a little bit different than it is for means. So if you look on your chart, we have the mean and standard deviation for a sample average. And we also have a mean and a standard deviation for a sample proportion. And there's the formula there. So it's similar, just slightly different way to calculate it. And here is how to get what we call p-hat, or the sample proportion. So it's all there again on your chart. It's kind of two different sides of the same coin. Calculated a little bit differently, but the big idea is still the same. So at this point you might be very confused about what's going on. So I'm going to try to clarify it with what we call a T-chart. So we have means on one side and proportions on the other. And I want to show you that they're kind of parallel to each other with similar characteristics, just calculated slightly differently. So a mean is an average, and usually the average comes with a standard deviation. So if you have x bar and sigma, or x bar and s of x, or mu and sigma. So you're always going to have a standard deviation that goes with a mean. A proportion, on the other hand, is a ratio or a percentage. So you might see a percentage. The standard deviation will not be given. You'll just be given p-hat equals x over n, or you might see a percentage of some sort in the problem. So if there's not a standard deviation, you're most likely dealing with the proportion. If there is a standard deviation, you're generally dealing with the mean. And it should be very clear in the problem if you're talking about means or proportions. So Chapter 8 is split in half with means and proportions, so is Chapter 9, and so is Chapter 10. So we'll constantly be distinguishing, are we talking about means or are we talking about proportions? The biggest difference is that a standard deviation is given for means and has to be calculated for proportions. So the standard deviation for a sample mean is sigma over radical n, which is what we just discussed in section 8.1. This is section 8.1. The sample standard deviation for a proportion is this new one, the whole square root of p times 1 minus p over n. And this is in section 8.2. So they both have a sample standard deviation, but they're calculated slightly differently. And finally, to check if they're normal. So a sample mean is considered normal if the sample size is at least 30, which is what we again discussed in section 8.1. A proportion average is considered normal if these two conditions are met. N times p times 1 minus p is at least 10, and little n is less than 5% of capital N, which is the sample is less than 5% of the population. So this is again in section 8.2. So we're still doing the same thing. We're still going to use normal CDF. It's just the way that it's calculated is slightly different. One is for means, one is for proportions. So hopefully that'll kind of help you distinguish the two. I'm going to leave that out to the side in case we need to refer to it later. All right, so here's an example from page 383. It says, based on a Gallup poll, Gallup is an organization that does a lot of surveys and polls, 76% of Americans believe that the state of moral values in the U.S. is getting worse. So right away, you have a percentage. When you have a percentage, you're talking about proportions. That's a p-value. Suppose we took a random sample of 60 people. There's my sample size. Describe the sampling distribution of the proportion, so they kind of give it away for you, proportion of the sample that believes the state of moral values in the U.S. is getting worse. So as soon as you see that percentage, or see the word proportion, or notice that in this problem there is no standard deviation. As soon as you see that, your brain should transition to the proportions. You're dealing with proportions here. So, in order to check the shape, we have to do these two checks. Is the sample size, 60, less than or equal to 5% of the population? Now, they do not give us a population size, so we cannot actually calculate this. We just have to think. Is 60 less than 5% of the population of the United States? Right away, without having to calculate anything, we should be able to say, yes, there are millions of people in the United States. 60 is a very tiny number compared to millions. So we don't have to actually calculate that all the time. Sometimes you just think about it and you can say yes. The other one we always have to calculate. So we're going to take n, which is 60, p, which we're going to convert to a decimal, 0.76, and then 1 minus 0.76, and we're going to see what we get. We did this back, I believe, in chapter 6. So 60 times 0.76 times parentheses 1 minus 0.76. Most of the time I do this in my head. Otherwise, you can just let the calculator. I usually do the 1 minus p and just change it over, or you can type it in just like that. You get 10.944. Is that greater than or equal to 10? Yes, it is. So whatever value you get, as long as it's bigger than or equal to 10, you're fine, and you can say yes. So if this is true and that is true, we can say that the shape is approximately normal. So again, the checks are different, but the idea is the same. The center of the distribution, which would be the mean of all the sample proportions, would work out to 0.76. And finally, the spread of the distribution is the new way we calculate standard deviation, which is the square root of p times 1 minus p. Now 1 minus 0.76 is 0.24 over the sample size, which is 60. So again, I just in my head worked out that 1 minus 0.76 is 0.24. You can type in 1 minus 0.76, it'll just be more typing. So we're going to do the square root, 0.76 times 0.24 divided by 60, and then close the parentheses. The calculator will follow order of operations, so we can just hit enter. Get 0.055. So we could draw a normal curve now that's centered at 0.76 with the standard deviation of 0.055. So everything at this point is the same. Once you figure out if it's normal, get the mean or the center and the standard deviation, from here on out it will be just the same as before. So let's see how this works. Example 4 says, according to the National Center for Health Statistics, 15% of all Americans have hearing trouble. So again, this is a percentage which tells us we're in proportions. It also does not give us a standard deviation, which gives away that we're looking at proportions. So we're not going to do the normal checks, we just did that. We're just going to jump right into a question. In a random sample of 120 Americans, what is the probability that at most 12% have hearing trouble? So we're going to jump straight to normal CDF. At most 12%, so less than or equal to 12%. That's going to be negative infinity to 0.12. So you always change your percentage to a decimal, 0.12. The mean is 0.15. And the standard deviation, you'll just type in that whole calculation, 0.15 times 0.85 over the sample size, 120. Now again, that's 1 minus 0.15. I just worked that out in my head. 0.85. I actually pretend like the 1 is a 100, and 100% minus 15% leaves 85%. So I would just always calculate that before you put it into normal CDF. It's just a small little way to help you save making a tiny error like that. So we're going to do normal CDF. Negative infinity to 0.12, so your percentages always gets changed to decimals. The mean is, or the average proportion is 0.15, and the square root, 0.15 times 0.85 over 120, and close it with 2 parentheses. Hopefully you can see that. Negative infinity to 0.12, 0.15 is the true proportion, and then standard deviation. And I got 0.1787, or about 18% chance of that happening. Now question B is a little bit different. It says, suppose that a random sample of 120 Americans who regularly listen to music using headphones results in 26 of them having hearing trouble. What might you conclude? Now I want you to notice that what they gave us was a percentage. The first question gave us a percentage. This question does not give us a percentage. We have to calculate the percentage ourselves. So we have to calculate the proportion of 26 out of 120. This is your X and this is your N. So if they give you a percentage, you can jump straight into the calculation. Otherwise, you have to calculate the proportion yourself, 26 out of 120, to get that ratio, 0.2167. So sometimes you have to get the percentage yourself by using X and N. You could put that in the calculator like that as a ratio, and it can calculate it itself. But let's see. So it says, what are we trying to conclude if this situation is true? Now, this is about 21 or 22%. Our true proportion is 15%. So on the curve, we're on the top side of the curve. So we're going to see how extreme this value is by doing normal CDF. This will be our lower bound, 0.2167. Our upper bound will be infinity because we're on the top side of the curve. The true proportion, remember, is 0.15. And our standard deviation We will let the calculator crunch that. And we'll see what we get. So we're going from this ratio to the right because this is above our true proportion. If it's below your true proportion, then you go to the left. But because it's well above our true proportion, we go to the right. And let's see what that gives us. So normal CDF, 0.2167 to infinity, 0.15, and the standard deviation gives us 0.0204. Well, what might we conclude? Well, 0.0204 is less than 0.05. So that means that we have an unusual result. And the book talks about different conclusions. I would conclude one of two things. Either listening to music with headphones severely increases your chance of having hearing trouble, or this number is too small. So it just depends on what you're arguing for. If you're trying to argue that listening to music using headphones causes more hearing trouble, well, then you have your evidence to prove your case. If you're trying to prove that this percentage is too low, you could also use this result to prove your case. So the book talks about different conclusions you can come to. All you need to remember is that anytime we get a value that's less than 5%, we have an unusual result and something weird is going on or something extreme is going on. All right, so I think I'm going to pause there and pick up the last couple examples in just a minute.